Well, the topic of this video is color in computer graphics. We've talked about it a little bit, GL color 3F, R, G, B, but if you're going to use color seriously in computer graphics, you really need more than just a little passing knowledge. There's two videos. I've broken this section up into two videos. The first one will be color theory. I guess you could call it that. And the second one will be rules of thumb and some of my favorite optical illusions. So let's talk about color. So any discussion about color has to begin with your eye. If you remember from 8th grade science, you have rods and cones in your eye. The rods are there to detect intensity. The cones are there to detect color. Turns out the cones are concentrated near the center of your retina. The retina is the back of your eye. The rods are concentrated on the periphery of the retina. And which really means that you are most intensity sensitive in your peripheral vision. And you can think of lots of good survival reasons why that would be the case. Sometimes at night you look up in the sky and you see a star out the corner of your eye and you turn your head towards it and the star's gone. And you turn your head away and the star's there again. That's what's going on. You have way more rods, the intensity sensitive part of your retina, at the periphery. Okay. Um, and your color vision is really concentrated near the center. And there are actually three kinds of rods, loosely red, green, and blue, not exactly. So let's talk about the color part, the cones. And are you equally sensitive to all wavelengths? And the answer is no. And really, you are most sensitive to intensity, grayscale. And that's not surprising. You have a lot more rods than cones, like 35 times as many rods as cones. So it's not surprising you're most sensitive to grayscale. What we've got here is there are, in the top row, there's 16 shades of gray from black, which in computer graphics is abbreviated K because B was already taken with blue. So they use the last letter of black up to white. So there's 16 phases, and sure enough, you can see the individual steps. And that's 16 steps. This is 32. This is 64, 128, and 256. Now, you're probably looking at this in a well-lit room, and we have the problem of, yeah, this was done on a program and then screen captured and put in PowerPoint. So there's some losses there. But if you were looking at the original program in a darkened room, you would be able to see at least all 128 shades and maybe 256, depending on who you are. We are most sensitive to grayscales. Next, in the color world, we are most sensitive to green. Here, again, same thing. There's 16, 32, 64, 128, 256. If we were looking at the original program on a monitor in a darkened room, you would be able to see, at least the 64 and maybe the 128, depending on who you are. Green is the color we're most sensitive to. It's in the middle of the electromagnetic spectrum. Kind of makes sense that we would have evolved good green vision. Red is in second place in colors. 16, 32, 64, 128, 256. I can see at least 32 here, and you might be able to see 64. Third place, last place, is blue. And there's really no nice way to put this. Our blue vision just sucks. Okay, look at that. Yeah, you can see the steps in the 16. Maybe you can see them in the 32, but really no farther. And so that's one of the rules of thumb of using color in graphics is if shades of a color matter, try not to use blue because really you don't see that many individual shades. It just all sort of mushes. Okay, also, how many pixels do you need? Well, it turns out if you have 20/20 vision, your visual acuity is about 1 arc minute, about a 60th of a degree. Now, what is visual acuity? If I put two dots here on the screen and Yeah, if you're looking at them from a normal screen viewing distance, you'll see two dots, but if you stand up and move away and move away and move away, eventually you'll only see one dot. Okay, your ability to distinguish two things is visual acuity. And so if you stand far enough away that the angle between those two is greater than a 60th of a degree, then you'll see two dots. If you stand far enough away that that angle between them is less than 100 or 1/60th of a degree, you'll see one dot. And so really you can kind of figure this out with pixels. Pretend instead of dots, those are pixels on the screen. Well, if a monitor has, say, 1600 by 1200 resolution, this is the required pixel density that you would need if you were really close. Like, hopefully none of you look at the screen from 6 inches away, but if you did, you would need a pixel density of 600 dots per inch, which is really a lot. Now, if you're looking at it from, say, a foot away or 2 feet away, this is what you would need. Okay, and one way to get that, of course, is to make the screen smaller. And so this is also a column of information. If I took the 1600 by 1200 on a 14-inch screen and looked at it from 24 inches away, yes, I would not be able to see the individual pixels, which is a good thing. Um, but you get bigger and bigger monitors, and then you go get a 60-inch monitor, and like, wow, you can see the individual pixels if you're too close. Okay, so computer graphics monitors use what's known as additive color. Additive color works like this. It's what's being done with GL Color 3F. Again, like we talked about before, there's red, green, and blue phosphors on each pixel. And if you excite just the green, well, you're going to get green. But if you excite green and blue, your eye's going to mush that together into cyan. Red and blue, magenta, red and green, yellow, and all three you're going to get a monochromatic color, black, gray, white. Okay, so this is really what Color 3F is up to. Playing with color combinations is really kind of fun. There's actually some neat websites that help you do this. Here is one of my favorites, and it will give you, you can play with that color picker program, but this website will give you certain combinations. And if this it isn't just this, it scrolls down and there's a ton of them. But if you see a color in there you like, it's like looking at paint chips, then there's the RG&B off to the side. Yeah, plasma displays and LED displays, they emit color. That is, if you go to Costco or Best Buy and you look at one of the LED displays, OLEDs, QLEDs, you will see really bright. Now, LCD displays, like most of us have in the labs, at home, in our laptops, those are basically gates. Okay, they are opening and closing gates, light gates, and they have different colors of essentially cellophane, and they typically have a um, a white light back behind the screen, and so it's gating light coming out. But plasma displays and LED displays emit their own color, and that's why they look so good, and that's why they're more expensive too. Um, But anyway, if you've not seen an OLED or a QLED display, go to Costco or Best Buy, somewhere like that, and take a look. It's almost stunning. You get up real close. I always, if I get up real close, I always get this feeling I'm sunburning. Is the intensity of what's coming out of them is so high. I'm not really sunburning. It just feels that way. So the LCD though, it's not as bright because it's got a, a white light back behind the monitor, and essentially the pixels are flashing on and off through colored cellophane, and that's how it's generating its colors. Here's something else we use a lot in computer graphics. It's called hue saturation value. The problem with RGB, it's what monitors do. Yep, that's great. But it's not the way we talk. You go up to somebody and you say, oh, that's a beautiful zero point 0.5 red, zero point 0.3 green, zero point 0.1 blue sweater you're wearing today. No, no, we don't talk that way. We talk in terms of a wavelength. Oh, that's a nice orange sweater you're wearing today. But we also talk in terms of brightness and saturation. Saturated colors are the most brilliant. Unsaturated colors kind of fade to gray. So people developed this thing called the hue saturation value color scale. It really is RGB. And you have a function in your sample code that will convert HSV into RGB, which you then can use with OpenGL. So if you would like to specify something in HSV, you can. And in fact, the second set of 3 columns in that color picker program are HSV sliders. Anyway, hue is the dominant wavelength and it goes around this circle, and that's kind of the color circle like you sometimes see in art classes. They draw this as a cone. White is right here. Black is down here at the tip of the ice cream cone. And so that means that all the colors along this line are grayscale. And saturation is a radius away from the grayscale. So down the middle, like right here, you get grays. And then as you go out this way, the colors become less gray, more brilliant. Okay, so that's what saturation is. In that function, SV and RGB are all between 0 and 1. H, because it's an angle, is 0 to 360. So anyway, you can use HSV RGB in your sample code if you would rather specify colors in this space instead of RGB. You still need RGB for color 3F, but you could start with something else. Yeah, I thought this was amusing. I was at Home Depot one day and looked at their paint chips and thought, wow, they have those kind of arranged in an HSV display. So yeah, even Home Depot likes that. Okay. Now, one of the reasons we also use HSV is in visualization. Sometimes we do a rainbow scale of colors to represent some value, temperature, stress in a structure, things like that. And so, well, this is great. We want to do this. And that range of colors is blue to green to red around the outside. So if I have a scalar value, say temperature, and I know the min and the max, if I take a given temperature, this is the equation to get the hue. Okay, so if I'm halfway there, I'm going to get 120. I'm going to get green, halfway between min and max. So anyway, that's one of the big uses for HSV is in displaying um, data values. Yep, there's the picker program, the third or the 3 sliders on the right. Those are HSV values. And there's other programs. Other programs have different ways of presenting colors to you. This is a program called ParaView. It just puts up a whole bunch of different color scales. There's more than this. And you get to pick the one you want to use. You can sculpt your own color too. Just get in here and start moving things around and sculpt your own color band. There's a program called OpenDX. See here, they're letting you sculpt hue, saturation, and values. Here's another website that's worth looking at if you like color. It's called colorbrewer2.org, and it lets you pick color schemes. And so here's one I was playing around with, kind of blue to light blue to light green to white. And it's not going to be so good for continuous colors, but for discrete colors, like things going on in individual counties on this map, it's pretty good. There's also some things in the Color Brewer program about what to do if you are worried about people looking at your display who are colorblind. So yeah, Color Brewer 2 is a very cool website. Now, you're probably thinking, wait a second, when I was in kindergarten, we mixed blue and yellow paint and got green. Well, that is called subtractive colors, and that's different. We just talked about additive colors because, well, that's what's on a monitor, and that's what you'll see most often. But when colors filter each other out, that's called subtractive. In the monitor way of doing things, additive color, well, you've got little colored dots next to each other. And so the wavelengths add up. So let's say that I've got white light, all the colors, and I've got a cyan piece of cellophane, and I put it in front of the white light. Well, why is it cellophane? Or why is it the cellophane cyan? It's cyan because it only allows blue and green to come up through it. Oh, okay. That means it looks like this. It blocks red. Now I put a piece of magenta cellophane on top of that. Well, why does that cellophane look magenta to you? It's because it only allows red and blue. Okay, well, cyan blocks red because it's only going to allow blue and green. Magenta blocks green because it's only going to allow red and blue. And so if I use these two pieces of cellophane together, the only color that can come out of it is blue. And this is called subtractive colors. And printer toners work this way, and paint works this way, like when you were in kindergarten. Color printing, all color printing, even though you may think you're sending RGB to your color printer, it's converting it into cyan, magenta, and yellow. Those are the primaries in subtractive colors. And if you mix cyan and magenta like we just did, you get blue. Magenta and yellow, you get red, and cyan and yellow, you get green. And if you mix them all, you get black, except it's hard to hold the wavelengths constant in the paint. And so really you get this mushy, deep brown. And so that's why color printers typically have not just cyan, magenta, and yellow inks, but black as well. And a lot of times on different things, ads in the color Sunday paper, a page of stamps, you'll see the color printing test is when they print this in multiple layers, they put these little squares on the side just so that they can look at it and make sure that the color printing is turning out like what they think it should. Now, when people talk about the science of color, they oftentimes draw this. And this is called the CIE chromaticity diagram. CIE, well, it's the committee, the International Committee on Light, except it's in French. So it's CIE. Light is éclairage in French. Um, and yeah, there's reasons it's horseshoe shaped, and I can go into that sometime if you would like. But essentially, it's very much like the wheel, the round circle in the hue saturation value diagram. Okay, because red starts here in the horseshoe, goes around this way, green is right there, goes around this way, blue is right here. It's stretched out in green because we're more sensitive to green. This diagram really was done based on human vision, and that's why it's not a circle. Circle was done for convenience in the hue diagram. This was done based on the science of human vision. There is a white. White is right here, or monochromatic is right there. And you can play games with this. If I put a color here, if I draw a line perpendicular boop, boop, to the horseshoe, that's the dominant wavelength of this color. If I draw a line from this color through the white point to the other side, that's the complement of the color. Okay, so yeah, you can use the diagram like this. What people tend to really use this diagram for is they will measure what color coverage different devices have. So I got a color meter once and measured it, and a color display Well, this was the green phosphor, the blue phosphor, and the red phosphor. So this triangle represents all the colors that particular monitor was capable of displaying, which you notice is a lot less than what the human eye is capable of seeing. So yeah, that's why people do this, is they're interested in what people can see versus what we can actually produce. I did the same thing for projected color slides. Yeah, that was actually a much smaller triangle. They call these things color gamuts. Means like a range or a coverage. The colored slides, and the color slides were shifted this way. You can see the triangle is not centered on the white point. And the reason is over here is yellow, because red is here and green is here, and the bulb in the projector is yellow. So it was artificially yellowing the colors that I was measuring on the slide screen. And here's one that we really, really care about. Color hard copy devices generally have color gamuts that are smaller than monitors, which are smaller than what humans can detect. Okay, sometimes you generate a display on a computer graphics monitor and it looks great. Oh, the colors are so brilliant. You can see different colors. And then you print it out and it mushes a bunch of the colors together. This is why. In general, color printer devices, color hard copy devices cannot mimic all the colors a monitor is capable of doing. And so you just become aware of that. There is another color space. I'm just going to mention the name. It's called LAB for no particular reason. L stands for lightness. A and B stand for, well, A and B. That's how they named the axes. This is used a lot in commercial color calibration. Like and then I have a meter. There's my meter that measures LAB. You pointed at something. I, I snuck into the OSU Beaver store and started pointing my meter at various articles of clothing for sale, and it was pretty consistent. This is where in LAB space, Oregon State orange shows up. Yeah, okay, that's kind of interesting. So anyway, you can also measure this. And this is, yeah, like I said, this is how they color calibrate commercial products. And so, okay, so that's the end of our color theory. There is a ton more. We really could spend almost 10 weeks doing nothing but color science. But I think that's enough for what we're going to be doing in this class this quarter. So stick around for the second video because there we're going to get into some rules of thumb, is how do we apply some of the theory we just learned in creating computer graphics displays.